Okay, welcome to another session of EL 164. This is Unit 4. Today we're going to talk about Chapter 11, math instructions. I'm going to incorporate some math instructions into some ladder logic and figure out how that whole thing works together. Okay, welcome to another session of EL 164. This is Unit 4. Today we're going to talk about Chapter 11, math instructions. I'm going to incorporate some math instructions into some ladder logic and figure out how that whole thing works together. This is not to be confused with our math lab is not supposed to be confused with meth lab. So make sure you keep that distinguished there. Okay? All right, moving on. Okay, for the first part of this, we're going to jump right into the math instructions. As you can see here, step one was select a new file, call it math, and create some new tags. Bam, we've got that nailed, so we're in good shape there. Next piece of this, we got to get another sealant circuit. That's what we're going to kill this sealant circuit every dang time we have class. Just make sure that when you walk away from this is going to be something that you're going to be very familiar with. So this is kind of a big deal in programming. So we're going to keep focusing on it. Okay, so the first thing we're going to do is we're going to start with our start-stop circuit. We're going to put this right into the main routine. So first thing I've got, as illustrated before, was a start-stop circuit. So we're going to go ahead and develop that real quick. So I went ahead and created that sealant circuit. Saved you guys trouble watching me do all that business. So now I've got the sealant circuit. Well, the next thing I have to do is I have to establish communications with the processor and download that information. Okay, as you can see, I'm in run mode. Controller's okay, I/O is okay, and by looking at this, you can see my rung is actually true, going true as I press the start button, and going false when I hit the stop button. Okay, I went through and labeled them all. I gave the start push button a name, the stop push button a name, and then I gave the output, I just call it math bit because we're dealing with math today. The next part of this is we need to add 5 to the output word when the bit is off, and subtract 5 from the output word when the bit is on. How are we going to go about doing that? So it's going to be just a series of adding some normally opens and normally closed contacts of this binary 4. Let's see how that's done. Okay, first thing I'm going to do is I'm going to grab a normally closed contact as I've done here. Next thing I'm going to do is I'm going to go over here to the math function, math compute. I'm going to grab what? I've got to grab a subtract, add 5 to the word. Oop, put it in the wrong spot here. So when this bit here turns on, I'm going to add 5 to the output word. So source A is going to be what? So 5 here. This destination, I'm going to move this to the output word. Output word, remember, that's going to be output data. Add 5 to this location, and we got to place it where? In the output data table. So we're going to move it right here to the output data table. So that gives us 5 plus this gives us this information. So when it's in the off state, it's going to subtract 5, and when it's in the on state, it's going to add 5. So as you can see here, what's going to happen is I'm going to put a 0 on this location. So now I've got all my outputs turned off. We're ready to rock and roll with this thing. I'm going to go and hit the start button. The start button is going to turn off, and then I'm going to populate this information. Now the thing with the Allen Bradley add commands and with a lot of other commands is that this command is going to take place every scan. So what does that mean? It's going to add 5 to this location every scan. So if I were to turn this bit off here, if I hit the stop button right now, you're going to see this information get populated rather quickly. If you were at my end, you'd be seeing all these contacts turning on and off in this processor like crazy. What's happening there is that it's continually adding 5 to it. So it's constantly adding 5 to it. As you can see, that number is increasing rather quickly. I'm sure we're going into overload or overrun and triggering that bit as well if we were monitoring that at this moment. But essentially what's happening is every time we close this contact, or in this case, turn this contact off, we're continuously adding 5 non-stop. So what do we got to do to solve that problem? We got to slip in a 1 shot in there. So let's go ahead and add that 1 shot in here. I go into add bits here, that 1 shot rising. Oop. I got to go into online edit. 1 shot rising. We'll put him right here after this guy. No. One shot rising. There it is, right there. Here I'm just going to grab a binary bit. So I'm going to come in here, grab. I got 4 used. Use 5. Let's see how it responds now. I'm going to turn this off. Oh, okay, it only happened once. I'll turn it back on. I'm going to zero this back out. And I'm going to turn it back off one more time. And look at there. We got a total of 5 in there. 101 is a total of 5. So we added it just once. Exactly what we're looking for. Now I got to do the exact same thing with what? The subtract, where I subtract 5 now. So I'm going to pause this for a second. Okay, I'm okay at this moment. I want to go here, go offline, copy this, paste this here, make him an XIC, make him binary 6, go here, make him a subtract function. Subtract this number. I gotta subtract 5 from this number. So I gotta put, remember it's always A from B. So I gotta subtract the output value, data. I gotta subtract 5 from that, right? Okay, let's download that and see what we come up with. Okay, let's see how it responds to it now. I'm going to hit the start button, bring in bit 4. It's at this moment you can see what looks like to be a negative number here in binary. Then I'm going to bring in a positive number. Then I'm going to hit the reset, this guy here, and we're back to 0. So by adding 5, had I put a 5 in here from the start, when I hit the 4, I go ahead and turn this guy on, 0, because it subtracted 5, and when I turn it on, I add 5. That's what I was after right there. So we're going from 0 to 5. As I make and break this circuit, we're adding 5 and we're subtracting 5. That's what I was after there. I'm going to switch this to decimal so it's easier to understand. Let's go ahead and do that real quick. I was thinking I could switch the output data word from binary to a decimal value, but it can't be done. So it only allows me to display it in binary format. So there we are. We're looking at the binary column of this information. So a 101 we know is 5, and all zeros is a 0. So that's what we're stuck with here. So It is what it is. It's not a bad thing, so good enough. So as you can see, I can flip it back and forth. A couple points I want to make sure everybody's aware of is, again, notice in two normally open contacts, I got a normally open start push button, a normally close stop push button, as you can see, is on all the time. And the seal-in circuit, the binary 4. When this contact closes, it brings this guy in. As this comes on, it turns on this guy here and opens that circuit up. And vice versa, when this goes off, closes this circuit, allows it to add one and open, or vice versa. It flips this back and forth, basically. All right, we finished part 2. Now we're moving on to part 3, developing a program using the compute instruction. Again, we're going to use another subroutine called CPT. Okay, so here we're going to create a new subroutine the same way we did it before. Just want to kind of go through this. CPT. For compute, or I could call it compute. So I can do that too. Either way, got a compute subroutine. Now what do we got to do here? We got to incorporate what? A subroutine call here. So let's see if we can find, where was that? Under program control. Right there. We need to get into here and jump subroutine JSR. Go to where? Compute, or CPT. And what do we got to do? We got to go ahead and remove these instruction parameters. Accept that. And there we are. Now we can go to our compute subroutine, and we are in business, ready to start developing some code. All right, so the requirement for this CPT was use input 8 to turn on the CPT. So let's go ahead and set up that. Input 8. And where do we find the CPT? But under compute math, CPT. Okay, for the destination, it calls out for digital integer 0. So let's grab that. And for the expression, it's calling for our old favorite Pythagorean theorem. For all those of you that may not remember your Pythagorean theorem, that's a squared plus b squared equals c squared. Well, to solve for c, of course, you got to have a squared plus b squared and the square root of those two. So let's go ahead and set that configuration up. Okay, one of the points I want to share with you is SQR is the square root symbol. What I got to do is I got to put everything in parentheses in the order I want them to complete. So the last thing that's got to take place is the square root. So I put a square root and then a first parentheses. Next piece of this is I got to have digital int 1 associated for A, and a dual integer or double integer 2 for B. So one of the things in the PLC world that they have in Allen Bradley anyways is they don't have the square function. So what is the equivalent to a square function? Is we multiply it by itself. So I'm going to go ahead and multiply this by itself. Now, one of the things I want to point out here is that it allows you to create a new tag or use existing tags. I can come in here and I can go double integer 1. Bam, just like that. I've got that in there. And then I go plus. And then I go here. And I take double integer 2, which represents B, times that by double integer 2, Notice this represents this parentheses represents these two units multiplied together. These parentheses represents these two units multiplied together. And this parenthesis and the next parenthesis I put in there is going to represent the square root of all this stuff together. So what it's going to do is it's going to take this guy times this guy, this times this guy, add those two together, then it's going to take the square root of all of that. That's how it represents that whole package there. So I'm going to hit enter at this point, and I get this. So as you can see, it looks like it's all happy there. I got an I here. Let's see if it downloads it okay. And it seemed to take it just fine. So now when I close this contact, what will take place is it's going to multiply double integer 1 times double integer 1, multiply double integer 2 by double integer 2, which gives the square of each one of those. Add those two together and take the square root. Now right now, all that information in there is all set to what? 0. So when I close this contact, oh, maybe not. Maybe there is a value in each one of those. Let's take a quick look here. I thought I had all those zeroed out. Maybe not. Oh, look at there. There are some numbers in there. So double integer 1 is 16. The double integer 1 is supposed to be equal to 5. Double integer 2 is supposed to be equal to what? 10. So double integer 0 is in binary. Let's go ahead and set him to decimal. I'll zero him out. Put a 0 in his place. Go back to compute. All right, so now I have a 0 in there. I have a register value of 5 in digital in 1, and I got a register value of 10 in digital in 2. So let's see what we end up for results. 11. So using Pythagorean theorem, you take the a squared plus b squared. So 5 squared plus 10 squared. To add those two together, take the square root of that value, and you end up with the value of 11. Pretty cool. It's actually 11 and then some change here. If you kick open your calculator, you will see a 5 squared plus 10 squared equals this. And then you take the square root of that value, and you get 11.18, blah, 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 blah. But as we're using real words, or excuse me, integer values with whole numbers, we only get the 11. So that's how that plays out. Okay, so we finished step 3 of the lab. Now we're moving into step 4. So if you completed the compute command, now we're working on the add instruction. The add instruction includes another subroutine, so subroutine add. We're going to use input 8 again to turn on the add instruction. Now we're going to use double integer 3. We've used 0, 1, and 2 for the previous command. If you decided not to delete that previous one, then we can go ahead and grab the next word available, which is 3. We're going to set that equal to 10. And then for the source B, we're going to count 0 pre, and for the destination, we're going to use count 0 pre or preset. After we completed that step, we are going to move on to designing a flasher circuit, 0.1 seconds on, 1.1 seconds off. That is, that's a pretty fast flasher. And then at the last piece of this, we're going to use a counter to count each time the flasher turns on. So let's move over to the PLC side and see if we can get some of this stuff going. Okay, as you can see here, I've created the AND subroutine, the add subroutine. In main routine, I went ahead and created the JSR to do the add, so that process is complete. So moving over here to the add instruction, I'm going to go over here. I'm going to create a new a new rung, excuse me. First thing I got to do is come over here, grab a contact and push that in. And then I got to go over to math compute, and incorporate the add statement. Here for the adds instruction, the requirements for this particular one was digital in 3, Source B was counter preset, counter 0 preset. Let's see if we can find that. And the destination is a counter 0 preset. Now, something I want everybody to be aware of, this is a very common practice in programming. For those of you who haven't programmed, this is a very common practice. If you want to add something to itself, say you want to keep adding 5 to something, in this case we're adding 5, so you go 5, 10, 15, 20 every time you trigger that. The way to do that is you add it to itself and you place the value in the same location. So what it's doing, it adds it to this, it places this information in the storage. So each time that this process takes place, every time you hit this button, it increments that count by 5. If you wanted to put the same value of 5 every time, you would change the value of this register here to some other integer, and then it would constantly put the same value. So every time you added 5, say you added 5 to 0, it put 5 here. So just a trick of the trade here. So we're looking at digital in 8 again. As you can see, I'm doing this all online. It seems to be working pretty effectively for me. I'm not having too many troubles with it here. So right now I've got a value of 0 and double integer 0. I've got so if I hit this add statement, it's going to be adding 0 to 0, right? So I mean, nothing should take place. So I close this. No change of state. So next piece of this is we have to do what? We have to design a flasher circuit. You guys remember how to do the flasher circuit? I'm going to go ahead and develop that real quick, and then I'll be right back. Okay, for a quick reminder, I want to set up the first rung here. We've got timer 1, which will be the next timer. Timer 0. I got to flash on for 0.1 seconds. If you remember, it's milliseconds, so it's going to be 100 is going to be 0.1 seconds. So here, all I got to do here is copy this rung, paste this rung here, change this guy to a, change him to a 0, and change him to a 1, and him to a 100. So now I've got my flasher circuit. As you'll see, this guy's going to start timing here. He's going to, as soon as this reaches 0.1 seconds, it's going to close this contact. This contact is going to time for 0.1 seconds. Open this contact, reset this timer, and start the process over again. Okay, as you can see here, we are flashing back and forth. And just keep in mind, when you see things like this happen, where you don't see it count to 100, it's because the scan rate of our PLC is way faster than our scan rate of our monitors and our computers of this data. So we're not seeing every number count from 0 to 100. It'd be physically impossible to see that take place. So that's why you don't see it reach to 100. You see the enables come on. Sometimes you see the done bits come on. Sometimes you don't. Depends on what the scan of the monitor is compared to what the status of those bits are at that time. So there we've got our flasher circuit. Now we got to come in with our counter circuit, right? So we got to come in here, add another deal here. Counter circuit CTU, counter up. So this is going to be counter 0, if I remember right. And this guy is going to be, after it is on for how long? For 0.1 seconds. So we need the on bit. So when we get the, this guy has been on for 0.1 seconds, excuse me. So I'm going to use timer 0, done bit. Okay, as you can see here, it's just counting up. That done bit is coming on pretty fast here. So let's see if we can catch up with that. So Oh, I got to put a value in here of 10, I believe. And let's see if I can catch up to it. Ah, see what I did there? I failed to do the one shot. What's happening is this ad is just it's doing multiple scans of ad here, just increasing the crap out of our preset. Let's do one more thing here. Well, before we add, I'm going to go ahead and incorporate this. Okay, so I got one shot in front of that guy now. So now we're not going to be continuously counting up. So now what I was hoping for here is to zero these guys out. And what you'll see is this count is taking place. As it's counting up, I can hit the input 8 button. Every time I hit it, what counts by 10. So it doesn't take long before I am above the preset value. And as you can see here, I'm staying ahead of it pretty easily. So every time I press the button, it adds 10 to it. Every time that done bit comes on, I'm basically pressing that button. Stay ahead of it. So that's pretty much all I wanted to illustrate there. It's just how easy it is to incorporate an add statement. Okay, we have completed the addition. Step 4. We're on to step 5. Here we're looking at the subtraction command instruction. It's very similar, and I assume everybody's probably getting the idea here. A lot of this is pretty intuitive. So we have a source A, a source B, and a destination for this as well. So in this particular case, we're going to have source A is going to be what? We're going to have integer 0. There's subtract from. So integer 0 will be our number we're going to subtract from. Source B will be what? It'll be a value of 1, right? Because we're going to subtract 1 every time the flasher flashes on. And then, of course, destination, just like the adds, we're going to be using the same integer value of integer 0. So let's go ahead and proceed to the PLC and get things rolling. Okay, now we're on to the subtract command here at the PLC side of things. So I'm going to go ahead. I already created the subroutine. I went in and made routine, and I created my JSR sub. So let's go into sub and see what we can do here. So first thing on this thing is I needed to come up with another flasher circuit. I've already created that flash circuit, so I might as well utilize that. Where did I put that? Over here in add. I've got this and this piece here, so I'm going to go ahead and hit shift. I get 2 here. I'm going to cut this logic. I'm going to drop it right into your sub, and I'm going to say paste here. Bam, so I got my 2 tires now. Using the same ones, if I try to duplicate them or did a copy and moved those here, I'd have to re-address them because the same addresses would interfere with each other, right? Because they'd be overwriting each other all the time. So I got to make sure that I use this, only these addresses once per timer. If I had the same address duplicated, this would no longer work. So the next piece of this, I got to have it set to 500, which I already do. I set that to 500 already. So I've got, so 500 gives me a ½ second delay there. So what else am I looking for here? I have a ½ second on, ½ second off to the flasher. I got to do a flasher on and a 1 shot to subtract 1 from integer 0. Okay, so what I got to do here? I got to come in here, create a new rung. Create, go to favorites, grab a contact, go to bits, grab a 1 shot, and finally, but last but not least, go to math compute and go to subtract and create the subtract function. I got one other piece of this I have to address too. What is that? That is use a compare command to stop the subtraction at 0. Which command should we use here? We could use a lot of different ones to make sure we stop at 0, right? We could say equal to 0. We could say greater than 0. Whatever we wanted to do. Something, some kind of limit even. We could say it's got to be at 0 in order to allow it to go. I'm going to go ahead and stick the greater than's in there. So I'm going to just say greater than. Let's see here. Go to compare. Go to the greater than. Stick that right in there. So we're good there. So now I can start addressing these things. First piece I'm going to do is at timer 0. I'm going to throw him over here. Drop him right in there. Give him a dot. Done. There we go. Next piece of this is going to be what? When integer 0 is what? Greater than 0. Bam, done. So now I'm looking at subtract what? I got to subtract from integer 0, right? So I'm going to come over here, hit this guy, go integer 0. I'm going to subtract what? A value of 1. I can put a 1, a decimal value of 1 in there. I'm going to put that right back into what? Integer 0 again, just like we did the add. Sweet. So now we've got that information. It's coming back and reminding me that I got to put a one shot in there. So at one shot, it's got to have an address too. I think 7 was the last one. I used 8 this time. So now I've got my flasher circuit. It's going to flicker back and forth here at a half-second interval. And I've got, so that's going to click this guy on and off. Greater than, as long as this value is greater than 0, it's going to continue to subtract 1. So what does that mean for us? So the value, when we reach a value of what? Greater than 0. So that means when we hit 0 here, when integer hits 0, we will stop subtracting. All right, let's download this guy and see how it all operates here. Oh, you know what I forgot to do? Is to set a value here of 10. Always forgetting something. Okay, so now we're, as you can see, we're counting down 4, 3, 2, 1, 0. Did it stop? It stopped. So we did it. We did good. We didn't go negative. We're all good. Everybody's happy. We stopped at 0. We're no longer. This is still flashing, but this is what? A is greater than B. No longer the case. So A is equal to B. So that's no longer on. So with that off, we're not subtracting any more numbers from this value. So that is how we do a subtract with a greater than command. I also learned a little bit about that 0 flag that we talked about a little bit in lecture. Let's play around with that a little bit. I just want to make sure you guys are familiar with it. I haven't used those a ton in Logic, but I think they are worthwhile to know. So in order to capture that information, I have to seal it in because it only happens for one scan. It only comes on for one scan. So if I come in here and I say I set this guy here, SZ, just to fool around with SZ, I'm going to grab some binary value. Let's say, how about 10? Oh, I just got him and pull him over. There we go, like so. And I'm going to, let's see here. Maybe I'll stop this. Oh, it's not going to like that, is it? I didn't accept this from. Unbelievable. So I had to accept the rung edits here. I didn't like that so much, so I had to get rid of those I's. So now I'm going to go ahead. I'm going to put a value of 10 in here. And I want to download this information and just see how that binary 10 responds. Now, what's going to happen is, as I mentioned in lecture, that Z bit is going to come on, but we're not actually going to see it come on. it's going to be a quick flicker of a one scan solution, and then it's going to come on and turn right back off again. So the reason I had to do a sealant around that is because it's only on for one scan. We would not have even seen this come on had I not did a sealant around it. So just to make you aware that if you're trying to use things like this 0-bit, it is not it's not black and white. Just make sure you understand that that component is like a one-shot solution for the software. So you see it scan from one scan, and that's it. So that's it. Okay. Okay, we just completed part 5 of today's lab. Now we're moving on to part 6, which is using the multiplication. Here we're going to be fooling around with multipliers, and we're going to be dealing with some flasher circuits again. Flashers work pretty nice for dealing with counters and timers and stuff, so it's a good tool to use on a lot of different applications. So we're going to play around with some flashers again, and we're going to use a counter again to give us some numbers to work with here. So we're going to count basically to 10 and back to 0 again. So we're going to reset it back to 0. And the last piece of this is we're going to take the cumulative value and multiply by 2. So we're going to be counting by 2s, kind of a cool aspect. So you ever run into a situation where you need to count by 2, this would be a great opportunity. So without any further ado, we're going to move right over to the lab portion, or the RS5000 portion here. Okay, here we are where I've already created the multiplication subroutine. Again, I've created the JSR multiplier. And I even actually cut and pasted these timers again over to this segment. So now I've skipped a few steps here to get us moving a little faster through this. So here I am. Next piece of this, I've got to have the timer set to 0.5 on, 0.5 off. I've got that already set. That's a good thing. Next piece of this, I have to count. I use a counter to count to 10 and reset back to 0. So this is kind of pulling back a little bit earlier. Some stuff we learned earlier, so let's see how that all plays out. Let's see here, we go to favorites, get contact in there, come over to counter, give me a CTU, counter up. Then I'm going to come over here and I'm going to create this guy here and go back to counter again, do the reset. So first piece of this is I got to get this guy here. When this guy here is done, I turn him on. Over here, this counter here, I'm going to use counter 5 just for a random number here. Let's grab just a different counter. We don't have to use the first one always. Okay, so we got counter 5 with a value of preset 5. Now we got to come over here when we reach the value of 5, or I think it's supposed to be 10, wasn't it? 10, I'm sorry, I guess I have 10 in here. Preset value of 10. When that value does take place here, so I'm going to come over and drag him. Done, of course. And this guy's got to be that counter 5 as well. So what's going to happen is he's going to count the value of 10. He's going to trigger the down bit. He's going to reset it back to 0, as you guys remember from the previous unit where we did timers and counters. Next step we want to do is we want to multiply by 2. We want to multiply this accumulated value by 2. How do we go about doing that? Well, it's just simply a matter of getting this information in place. So let's go ahead and say we could put a contingency in front of this. So I don't know, why don't we go ahead and do that? So I'll go here. And then I'll go over to multiplication, math, compute, multiply. Here I'm going to just come in here. I'm going to grab this guy here, drop him in there. This guy here. I got to multiply what by 2? I got to take counter 5. Dot ACC, right? The accumulated value of that. By 2, and I'm placing the output of this guy to what? The output data table. So So we're going to count by twos in binary. Kind of a cool deal. So here the results will be out on the output table. All right, let's see how this whole thing plays out over here. Put this thing in run mode. So here we are, we're counting up to 5, 6, 7, 8, 9, 0, 1, 2. Remember how that reset works? It's triggers it the second it sees it, so you don't even get to see it on the computer. And here we are, we're watching this thing count in binary by twos. That's pretty cool, huh? So we're counting basically we're really seeing 1 to 9 in binary here. So that's how it's actually working, counting it every other digit by that. So kind of a cool way of doing it. So that is using the multiplier. Okay, here we are. We're on, we finished the multiplier in step 6. Now we're on to step 7 of the lab. Here we're going to go into division using the division command. We're also going to create a subroutine called division. We're going to use that same flasher again, so that flasher circuit works pretty handy throughout this whole program to help keep things organized. We're going to use a flasher program and a one-shot to trigger the division command. Here we're going to divide by 2. We're going to set the digital integer 6 to 100, and we're going to put the results in digital int 6. So what we're basically going to do is going to divide 2 by 100 and place the value in the same location. So it's going to continuously divide down till it gets down to 1. Once this reaches a value of 1, we'll stop the process. Then we'll multiply that value by 100, and then we'll start the process over again. So bear with me, and I'll start developing this code here. Okay, so here we have the timer on, timer off flasher circuit, or timer on flasher circuit, excuse me. We have the division subroutine developed, as you can see here. And in the main routine, I created the division JSR. So we're all good there. So all I'm going to do now is just use a flasher with a one-shot to trigger the division signal. So let's see here. Let's go about doing this. Got this here, bit one shot, and I need to set up it so it only it only does it till get a count of 1. So I got to use a compare. One of the common things in industry is using not equal, so it's on all the time except when it's equal to this. So this is exactly what I want to do. I want it to be running all the time except when it equals to 1. And then I'm going to do a division, do a math command. So do a division here. So here I'm going to use here I'm going to grab a binary value. Here I got to use integer 6, double integer 6. When it is not equal to what? A 1. And here I'm going to take double integer 6. Divide that by what? By 2. And place the results in double integer 6. What I'm going to do is go ahead and duplicate this rung. Paste rung. I'm going to flip this guy to a normally closed. I'm going to delete this guy. I don't need a one shot there, and he's supposed to be on the other side of that guy there. So there we go. And this is supposed to be what? Equal to 100. It's equal to 100. I want to make sure that I'm multiplying by 100. over here to the multiplication guy here. And I want to multiply by what? Not by 2, but by 100. So let's see how that all plays together here. Okay, so right now I've got this thing flashing back and forth. As you can see, I got not equal to 1, equal to 1, divide double integer 6 by 2, place it in double integer 6, divide, multiply double integer by 100, and so I put a value of 100 in here. Let's see what happens. So there she goes. Yeah, looking for the value of 100 in there. Once it enters that, then you get a continuous operation of counting from 100 down to 1, back to 100 again, using mathematics. This is something that I think I mentioned before in the past. Is I prefer using math over counters. This is not necessarily the most efficient way to do this kind of thing, where you can do add 1 and subtract 1 and all these different ways you can come up with different values. But it gives you a lot more flexibility than using counters. So that is the conclusion of this week's lab, dealing with mathematics. We're just we're dealing with the basics here. So if you have any issues or concerns regarding any of these points, I'd be happy to review those with you. We'll look forward to seeing you guys, or hopefully seeing you guys on campus soon. We're talking second half of summer now. We might be able to get back on campus for face-to-face meetings. So you guys enjoy the rest of your summer, and we'll catch up with you soon. Talk to you. Bye.